So we'll start the class in a few minutes. Uh, so let us start. So first of all, I would introduce myself. I am Niloy, UTA for these courses, Conduction and Convection Heat Transfer. So I welcome all of you to this live interacting session. So this is our ninth live interacting session. Already we have completed so many live interacting session on this fundamental concept regarding this conduction and convection heat transfer. So I hope that you have gone through this course uh, by the instructor Professor Chakraborty and Professor Shum, and hope you will find the course interesting. So in this courses, basically our objective is to build fundamentals in your concept. So that is our motto. So I am here as you TA to solve some numerical problem and giving you the idea how to approach this numerical question. I think after this session you will get to understand how to solve the numerical question on this topic. Even you can solve the assignment, right? So you know about this importance of this course. That's how you need to correlate this course with daily life. So that is it. And also if some of you have enrolled for this exam, so the exam date is coming. It is on April. So I suggest all of you to please go through these courses, check whether any issue is there on your fundamental, and if you are able to solve the numerical or like that. And if you are not able to solve any question, please raise your concern to me. You can also reach out to me through by mail or WhatsApp. Okay. So in the previous classes, we have discussed about the thermal boundary layer and hydraulic boundary layer and the concept regarding this, right? So in this week, we will go into an advanced course, which is the internal force convection. So see, it in the first few classes we have talked about this conduction, and after that, once we have gone into this convection, we get to know that the convection is not a solo phenomena. It consists of both conduction plus fluid motion. So that is, it's not a fundamental heat transfer mechanism. It is a combination of the conduction plus fluid motion. As fluid motion is there, so there is force motion, like what you know, the force and natural convection. So if I talk about this natural convection and force convection, I am giving you some example or hint, like say say if there is a cup of tea, and if you just kept it in the room for some time, it will get cool. Why it is getting cool? It is getting cool because of the natural phenomena. That is the heat from the tea just released to this atmosphere. That's why it is getting cool. So this is a natural phenomena. But if you are blowing air over this cup of tea, then it's a force mechanism. And because of this, it is known as force mechanism. So now in the case of a cup of tea, if we blow the air above this cup, so it's a external force convection. But today we will be dealing with this internal force convection, right? So up to this we will discuss. So where we will find this application in this concept of this internal force convection, you will generally find this application in pipe or even in duct. So this is some of the real life example where you will find, like in case of the pipe, most often you will find this circular pipe. So most of this mechanism or most of the numerical or fundamental concept is on this circular, and also you can find some numerical on this rectangular or square duct. Okay, so this is the most common example. Okay, now coming, I'm just recapping few of the earlier concept, like if I talk about this is a plate. Say if this is a plate, so what we have, and there is fluid flowing. So you have got two types of boundary layer. One is hydraulic boundary layer and another is thermal boundary layer. The hydraulic boundary layer is because of these gradual changes of this velocity with respect to the wall, which we known as zero slip condition, right? So check if I draw the velocity profile in this line initially, you will find that at this point it is almost zero, and after that this velocity increases. Okay, so it's there is a sudden increase in the velocity initially, and after that it almost remain constant. So, but after a few distance, you will find there is the decrement is quite slow. So, like this way, and after that it will remain fixed. So that types of phenomenon. So you see, if I draw a boundary layer, you will find I'm using another color. So if you see, if you draw a boundary layer, so at this point you see this velocity is almost reaching the maximum value. So similarly in this point it is reaching like this, and after that it is getting constant. So this is known as hydraulic boundary layer. Similarly, there is a concept of thermal boundary layer, right? So in case of thermal boundary layer, maybe so in case of thermal boundary, maybe say if the thermal boundary is forming like this way also. So this is almost a similar types of curve, but you can't know the thickness of which layer is more or which layer is less. So that's why there is a number, Prandtl number, which we have studied, which is the hydraulic, which is the hydraulic thermal boundary layer thickness by thermal, sorry, hydraulic boundary layer thickness by thermal boundary layer thickness. So if the Prandtl number is more, what it indicate? It indicate that the hydraulic boundary layer is thicker compared to the thermal boundary layer. And if the Prandtl number is small or less than 1, what it indicate? It indicate the thermal boundary layer is thicker compared to this your hydraulic boundary layer, right? So that thing we have already discussed in the earlier classes. Now I am talking about this fluid flow through a pipe. Okay, so this is a pipe. Let us say this is a pipe. So if there is flow coming from this direction, say this is u infinity, it is coming. So at this, say I am taking a section. This section I am talking about. Say this is a section. If I take this section, it is section 1. At this section, what happened? Because of this wall, the velocity of the layer is 0 almost, and after that it will gradually increase. Say this is the central line here. So what will happen? In the central line, though the velocity is maximum, it will gradually reduce as you move toward the wall. Similar is the thing on the both side of the wall. So that is how the velocity distribution is there. So now see one thing. If I draw a line here joining this velocity, so you will get a profile, right? So you will definitely get a profile. So the velocity, if someone asks you to find the velocity, how will you find the velocity? So this point, this is your V max or U max, whatever you say it is U max. This point is U max definitely, but you can't say the velocity of this whole fluid as U max because you need a representation, right? So that's why you need the average velocity. So the average velocity, if you find out how you need to find out this average velocity, so there is a certain way to find out this average velocity. So before this, let me tell you one thing. So you know this mass flow rate m. For mass flow rate, you know this is rho a into v velocity. So the rho area into v. So what is that value? So let us assume this v, instead of v it is u, because I represent the velocity as u. Okay. So what is the u we consider in case of mass flow rate? In a tube, say it is a tube. It is I am talking. This is a tube or circular tube pipe. So the mass flow rate, in the mass flow rate, what area you are taking? You are taking the cross sectional area, right? And the u you are taking is the average u. So you need to find out this average u. But here this velocity distribution is there. How will you find out? So for this you need to integrate. You know that if there is a variable in a flow field or anything, so in that case you need to integrate. How you integrate? So this rho, you know this, you just have to take a small area in the domain. You just have to take in a small area. Say this area I am talking about. And after that, in this small area, let us assume this velocity be u r, okay, into area at this small region is say a. dA is the area in this small region. So if you integrate this whole thing, you will get the mass flow rate. So this is not the exact, this is the generalized formula, but if something is given like that, then you have to integrate this thing. So for this integration, you need the u. What is u? You need to find the value of u in terms of radius, right? So u should be a function of the radius or diameter of the pipe, whatever you want. Similarly, the area. You d area, you know it is pi r square, so d of a means derivative of pi r square you need to take. So all the variable are should be in r terms. So accordingly, you know, if this is r, so the capital R, so the small value r changes from 0 to capital R. Accordingly, you can find out this mass flow rate. So that is one option, right? Another option, if you doesn't require this mass flow rate, you require only the velocity. So for this velocity also do the similar thing. How? Just a minute. So V average I am talking about, U average. So for this U average, what I will do, I will take this whole mass flow rate into divided by, say this mass flow rate is rho a v. So if I take this integration of all this into dA by only rho into dA. So that will give you this average, right? Now say it is a circular pipe, radius r, say. So in that case, can I write this is rho u? I don't know the value of u. A I know generally A is pi r square. So dA is 2 pi r into dr, right? So can I write in place of dA it should be 2 pi r. Just a minute. It should be 2 pi r dr, right? So now you can integrate what is the value of r range from? It is from 0 to r. Similarly here also you can do area 2 pi r dr, r is 0 to r. So accordingly, say rho is constant. Let us assume rho is constant or it is an incompressible fluid. Let assume, I am just assuming this thing. So in that case, the rho will come out, right? Hmm? Into 2 pi will come out, and what will remain inside? Into r dr 0 to r. That means you need only the value of ur. U should be a function of r. So if in the question it is given the ur, then you can accordingly find out this value, right? So similarly, if you integrate the denominator, you will get 2 pi r dr should be r square by 2, which is your, okay. So accordingly, you will get it as, so see how you find out this average velocity, that is important. You just need to integrate this mass flow rate by only the rho atom, okay. So if someone forgot this formula, how you remember this thing? Say this is mass flow rate into rho AV, you know. So as you need U, so in the bottom there is rho and A. So in the dimensional analysis, the unit of rho and rho will cancel out, area and area will cancel out, only U will remain. So that's how this thing comes. So this is known as your average velocity or or mean velocity. So sometimes it is also represented as u mean m. So it depends on you how you need to represent this thing. Okay, is it clear? So why we have studied this mean time? So why we have studied this average velocity? Because this average value, if I talk about an incompressible fluid or incompressible flow with the same cross-sectional area, so it is quite convenient for us to work with the average velocity to find out all these parameters like mass flow rate and all this. So that's how this thing is required. If someone calculates the mass flow rate like this way, it is also correct. And if someone finds by finding U average and this formula, it is also correct. Okay. So for the velocity thing, it is, I think it is okay to you. Now I am talking about this temperature profile. So say if a fluid is heated, so a pipe is there. Let us assume this is a pipe and through this pipe fluid is flowing. Okay. Say this is the temperature at the wall. TW on both sides it is TW say. So say it is heat. I am just heating for in it is a case of heating. Say okay. So what will happen in case of heating? So if I find out this temperature profile. So how this temperature profile looks like? So here the temperature not arrow because temperature in the velocity there is an arrow because it is a vector but temperature is not a vector, it's a scalar quantity, so it should be line. So and below this from the fundamental understanding you know that this temperature profile will decrease and again in the center it will be the minimum and again it will increase, right? So this is how the profile should look like. So this point is your T minimum. Okay. So, but one thing I just forgot in the so the T average U average value I got. So if someone have to represent this U average value in the curve, how to represent it? So this U average value, say in this curve, if I draw a line, so the U average value is somewhere here. So all this line, say this point and this point. So this line is corresponds to your U average. This is your U average, right? Similarly, in case of temperature, we also need a mean temperature value or bulk fluid temperature because as inside this tube the fluid is flowing and we are also applying heat, so we can't say the temperature of each and every point for we can't take the temperature of each and every point inside the domain. So what we are doing, we will have to take the average or mean temperature. Say Tm is the average or mean temperature. Okay. So this Tm is the average or mean temperature. Now, how you need to find out this T average? So, in case of velocity, what you do, you just take the mass flow rate. Yeah. So, because the velocity is related with the mass flow rate, and the energy and sorry, and the temperature is related with the energy, right? So, can I write? That means say if E be the energy, say this is the energy of the fluid. So, it should be m dot Cp into T mean. Can I write? So, but I don't know the value of Tm. So, how you need to do? You need to integrate. So, for this integration, what are the variable? The Cp, say the mass flow rate also you know in the earlier slide how to find out this mass flow rate. So, this mass flow rate is rho ur into area dA. This is for m because we know m is rho ur dA. So the Cp should be there and Tm should be there. So as integration is there, Cp is a constant and Tm here is I don't know the Tm. So the we have to take a small section where T is a function of R, like like this way. Say this is a small section you are taking. This is the Tr is the temperature of the profile. Temperature profile. So accordingly you can calculate if you know ur, if you know tr, you can easily find out. Or the another thing is that if you know another way to find out is that say you know the value of u average, so you can directly put the value of u average here. In this way you can also, but this is a fundamental approach. So similarly, like the previous way, if you have to find the t mean, so it should be integration of this one into only the in by only this one MCP. So I can write, or also someone can write it integration. If I write it in integration form, so CPTR into DM. Okay, TR into DM. Similarly, CP into DM. So this is how we derive this thing into CP into TR. We know that DM is basically your rho u sorry rho ur into dA is you know rho ur into 2 pi r dr into 2 pi r dr, and the integration is from 0 to r. Similarly here it should be from Cp into rho ur into 2 pi r dr. So say for some reason Cp is constant. Okay, the rho is constant. So the other thing, if you integrate, what you will get? You will get the v in a, also you say that this is Cp into dm. So this dm in a, also you can write it as into rho. Area would be pi. This one is pi r square into v average, like this way you can also do. But that is not required. Based because if you know v average, you can directly put the v average here. How you can put the v average? Because uh, you also know that this m is rho a v average, right? U average, sorry. So u average, you if you find out u average, you can put m dot. So if you find out this m dot, you can easily find. So this rho Cp means integration of dm. If Cp is constant, integration of dm is m dot, right? So accordingly, you can find Cp. No need to write this one into m dot. Like this way, you can also do, but it's up to you how you need to solve this one. So this is how you need to solve this one. This is for the T mean or T average I am talking about. So in sometimes what student did is the student take, say they know the mean value, they know the world temperature, they just take the average of this one T mean plus TW by 2. That is the average value, but it is not the correct way to interpret. This is how you need to interpret this thing. I think you got it, this thing. Okay. So check this thing. Let me know if you have any confusion up to this. I'm giving you 1 minute time to look up on this. Okay. So we are moving into a next concept. Say this is a pipe. I'm talking about this is an entrance region. Say this is a pipe I'm talking about. In this pipe, the fluid is flowing. So initially what happens? Say this velocity. If I talk about this at the entry, the velocity point almost at each and everything will be same. So you will hardly check any, you will hardly find any changes in the velocity profile. But after that, if you see, because of the wall effect, there is, so you see, so the profile that is generating here, it should be somewhat like this. Okay. So as you move further, you will find the profile is somehow more. Similarly, if you go here, so at this moment it will be, and after a few moment it is a fully parabolic profile. So as you move further, this decrement with the wall, I'm talking about this velocity profile. Say because of this no slip condition, what will happen? There is a drop in the velocity. So it is initially say it is zero. From zero it will increase suddenly. It will in the initially it will suddenly increase to the maximum value. And after that, as you move further, again this decrement is up to a certain level. So because of this, if I draw this thing, and after a few certain distance, it will gradually increase and reaches the maximum value only at the center. So it's a fully parabolic profile like that. So and after that, it remains same. If you draw anything after that, it is fully same. There is no change in the profile. So you see, initially there is, if I draw the, this is the average value, this is your V average here. Similarly, here somewhere in between this will be your V average or U average, whatever you say. Similarly, here this is somehow where you will get U average, right? Here also this is your U average, this is your U average, right? So if I connect 90% say where at this point almost it reached the maximum value. So if I connect this point here at this point and here it is connecting at the center, and after that it is like this way. Okay. So better to use another color. Similarly from the bottom, if you if you see here it is almost reaching the maximum value, here it is also reaching, and in the center here it is getting mixed. So you see the profile is somehow, if I draw it separately, you will find that the profile is looking somehow like this. After a certain distance, both the boundary layer reaches the same value. So up to the point, this point, what will happen? There is a boundary layer changes. So in this point the velocity changes like I have shown here. If the velocity change sudden, there is a sudden change in the velocity profile, but as you move further the changes is in a uniform manner, like it will gradually increase, and in this region and after a certain distance there will be a fully parabolic profile. Okay, so up to the region from where this fully developed or parabolic profile you observe, that is known as your fully developed flow. This is known as fully a flow or region. Better to write, I am talking about this region. This is your fully developed region, and this is your developing. This has not developed yet. This is known as developing region. So this thing I am only talk U average. That means it's hydraulic hydrodynamic. So the main thing is that inside a fluid, inside a tube, if the fluid is flowing, what will happen after a certain length? The profile of the fluid should be a parabolic, and from this point we consider it should be a fully developed flow. The fully developed, why the fully developed flow is necessary? Because say if I talk about a laminar flow, so if you in the nature, if sometimes you see if the water is pouring from a tap, you see there is no changes you see in the water. It's looking like it is getting freezed. The water that is dropping from the tap, it is sometimes looking like it is getting freeze, but actually it is not. It actually in that cases there is no disturbance. That means uniform velocity profile you will observe. So you doesn't under though there is velocity flowing, and though there is fluid is flowing, but you can't see the changes in your naked eyes. Okay, so that is the basic difference. So similar thing is for the thermal boundary layer. Okay. If I draw for the thermal boundary layer, let me draw it for the thermal boundary layer. So in the thermal boundary layer, so initially temperature at the entry, the temperature is almost, you see it is almost, there is no such dropped you will observe. But as you move further, so what will happen? So initially, though the temperature at this point is here, it may, I am talking about the cooling purpose. It is not heating. That means here the temperature start increasing, and after that it is fixed. And it is using another color for your understanding. Say it is something like this, and again this is a straight line. So similarly, if you see here up to this, then a straight line like this way, the temperature profile. But after a certain time, you will see that a fully parabolic, almost a parabolic profile you will observe. So that means you got to know that it is getting fully developed region. That is also known as thermally fully developed region. Okay. So that's why this is quite essential. So this is for thermally So thermally. Okay. Now let us talk about this velocity profile and all these things. In the previous cases, like if I talk about this is a pipe, and I have also got to know that this is the temperature, this is the thermal boundary layer. Right? So I am plotting few section here. This is one section. This is section one. This is two. This is your section three, and this is your section four. Okay. So there is a central line. The thing is that from the previous one, you see what we have got, that at the central line, the velocity initially, whatever be the velocity, because your main objective is the total velocity or the average velocity should be same. U average should be same for this incompressible. So the profile, whatever be the summation or whatever be the integration of the profile, that should be fixed here. So at the central point, if it is here, say look into this. So here the changes is quite less and it is only uniform. So that means here the average value, or what I can say, just a minute. Huh. The central velocity, the at the center of the whatever with the velocity you reach here and whatever with the velocity you reach here, it will be more. It's like that. See, if I am just giving you an example, if there is a value like 1, 5, 5, 5, sorry, 2, 1, 2, 1. So if you average it out, this is 15 and 21. So you can find out this, you can average it out. And in case of this one, it's the profile should be like 1, 2, 3, 4, 5, 4, 3, 2, 1. But see the distribution here, if it is 5, that means in a, any every particle, say here a particle is carrying this velocity, the layer of the fluid is carrying this velocity, right? So in these cases, if there is a gradual increase in the velocity, that means the total energy that is carrying in the previous case and the total energy that is carrying in these cases, it should be almost, the energy should be same. So for this reason it shouldn't be 5, there should be 6. To match up with, there should be a value much more than this one. So it should be 6, 5, 4, 3, 2, 1, like this way the distribution should be. So that's mean at the central line the velocity will increase. Initially whatever the value, if at this point it is say u central line 1 and u central line 2, so you see that u central line 2 should be greater than u central line 1. Okay, so that is the thing. Yes. So for this reason, and after that, if it is a fully developed flow, in the fully developed flow you get a value say uc3. So at this point, after this point, there is no such changes you will observe, because already the profile is same. So that's why what I am saying, that uc1 and uc2, so that uc2 should be greater. And in case of uc3 and uc4, as it's a fully developed flow region, so that should be almost equal, right? So let me draw some profile for you. First is the U profile. So that is with length. So U profile, if I talk about this U profile and then also say pressure and then tau profile. So these are the three profile I will plot here. So check in this, already I have discussed about this U. So at the center line U, what you observe, if I take the center line, initially whatever with the value, it will gradually increase, and after that as it reaches this fully developed flow, fully developed region, then it getting constant. So the profile should be like this one, right? And for the pressure, so how should be the profile looks like? So it's an important thing. Can you guess how you need to do this thing? So for this thing, see in this region, I am just taking a small region in this fluid flow domain. So here there is a pressure. See, the pressure is P. So what should be the area? Area is A, right? And in this region, what should be the pressure? It should be P plus del P del X, because at a distance X, this is a small distance X into del X. And what is the pressure force? The area should be same. Now say there is a shear force tau W. So what should be the force? It should be into the perimeter into del X. So this perimeter, say this, I am representing this perimeter as small p into del X, right? So what should be the force inserted into this control volume? Pa is given into this control volume. It is supplied, and in the outlet this force. So this is in the outer direction. So I have to subtract these forces, right? And also the shear force is on that direction. So that force, sorry, if the flow is in this direction, so then the shear force, let's correct this figure, let me. So there should be the, because the flow is in this direction, so when will there be a flow? If there is a pressure difference, then there is a flow, right? So this P is, small p is your perimeter, so that should be equal to 0. So this PA will cancel out, right? So you will get only del P del X A equal to tau W P, or you get this tau del P del X A by P, which is your perimeter. Here P is the perimeter and this is your pressure. This is your perimeter, right? So just remember this thing. So from this, I also got to know that the tau and pressure. So whatever be the changes in the pressure, there or the shear stress, there should be almost same, because it is directly proportional to this one. So the nature of the profile should be same. Now I am applying, as it's a tube, I can apply this Bernoulli's equation. So this Bernoulli's equation, this is pressure Cv, this is P. Just a minute. Hmm. So what I'm saying, Bernoulli's equation. Now I will be applying this Bernoulli's equation. So P plus, I can write it as, in terms of density I am writing, okay. And this, there is a three terms in the Bernoulli series. One is a pressure term, one is a kinetic term, next is a datum line or the datum term. So that datum term I am considering as a constant because the pipe is in a same inclination. So I am just writing only this pressure term and this velocity. This is your density. Okay, this is now if I derivative this thing with respect to P, what I will get plus rho by 2 into 2u, say it is u because I am taking u, 2u du dx equal to 0, right? So from this thing, if I write du dx, this is your minus by 1 by rho u. So it is all, so that if you see this value, so I need to find this only change of pressure with respect to distance. So the dp dx I require. So from this reason also you can see that this dp dx, this is minus rho u du dx. So what is the, this indicate? This indicate that with the change, that means whatever be the energy required to increase this velocity, that should be compensated from this pressure energy. That means it should be inversely related. So this pressure profile should be like this way, because say this is your fully developed region. So initially it will be a profile like this one, and after that it is a straight line. So similarly, as I have also got to know that the shear stress and the pressure terms are directly related, so easily you can plot this thing like this way. So I think you get this thing. Please let me know if it is clear to you. Okay. So now we will be moving into few numerical question, and after that again we will goes into this concept. So this is our first question. Please look into this question. I am giving you 2 minute times to solve this one. So it's the same thing, same concept that I have discussed a minute back. Okay, so anyone? Good. It is false. So why it is false? Because already I have told you that if this is the profile, so initially this see, remember one thing, whatever be the velocity, what is velocity basically means? It basically means kinetic energy, right? So it is energy. So what may be the energy entering the system at any section, if you find out the total energy, that should be same, right? So in this reason, that's why if at the center line, before reaching the fully developed flow, the tendency, what is fully developed flow, or what is a thermal boundary layer? The thermal boundary layer basically is a layer that we imaginary line that we have generated based on this viscous nature of the fluid. Like in the here, because of the viscosity, the velocity is almost zero, and after that it suddenly increases. So because of this sudden increment, we just plot a point, and similar to each and every layer, we just plot a point. So what happens? So initially, it is observed that whatever with the velocity at this point, and as you move further, so this velocity is a little bit higher, because at this region the velocity profile, there is a slow increment in the velocity profile. Because of the slow increment, that means if there is it is 1 2 3, and at this point if it is 1 then 5, so there is a sudden increase. So that increase, that incremental value is shifted to the central point. Okay, so that's why this velocity increases. So if it is 1 point and if it is 2 point, section 2, if they are talking about, so though u2 is greater than u1, but at this point after it is reaching this fully developed flow, the velocity is fixed, there is no change with x. That's why only up to this developed region the velocity profile changes with x. After that there is no dependence on x. That's why the correct option is option B. Good. Good, Shashwat. Next question. And now, please, uh, this is also the same question based on the previous one. So, can you answer this one? I'm giving you again 2 minutes. There are 5 questions from the first one. I think if you understand this concept, you can easily answer these 5 questions. Shashwat, any idea? Any guess? And the first option, okay, not an issue. The first option is that the shear stress at the first layer. This is one layer. This is one. See, you remember this profile, velocity profile, shear stress, all this profile? Can you remember what I have plot? So U, if first I am plotting about this U, what happens to U up to this thermal, up to this fully developed flow, below before this fully developed flow, it will gradually increase, and as it reaches the fully developed, it remains constant. Next is the, if I talk about this pressure, so what will happen initially, their pressure is high and there is pressure drop, because see from this Bernoulli's equation what we get to know, if the pressure is increasing, pressure drop is increasing, that means the velocity is decreasing. It is inversely proportional, right now, because in the Bernoulli's equation two terms are there, what three terms are there. If you forgot about this datum line or which we can say as the potential line, so there is two term, one is pressure term, one is velocity term, and so the sum of the two should be constant. So if the velocity term is increased, the pressure term should need to be decreased, it should be inversely proportional. That's why this P is initially it decrease and after that it remain constant. Then in case of tau also, right? It is almost like this. So this profile you remember. Now you tell me one thing. Basically, if I talk about this tau, what is tau? Tau from this viscosity, you know, it is mu du del y in the y direction, right? So the question is that tau 1 and tau 2, it is greater as the next statement is as the fluid enters the channel, the local boundary layer tends to 0 at this position while UC is finite and tau W become infinitely large. So initially see at this point at the entry point the tau is the maximum, right? Okay. So and after this, so this tau become infinitely large. The first statement is verified. UC is finite. Yes. At the entry UC is finite. And just say that the it tends to 0 at this position at the point where the thermal boundary layer is 0. That means this point they are talking about. So statement 2 is correct or no? Correct. Now I am talking about the statement 1. So I am just taking 2 points. This is point. This is two section. This is one. This is two. So now you say which tau is more? Tau 1 is more or tau 2 is more? So then it is wrong. So which one would be the correct answer? D. So based on this, you can easily answer this one, right? And also you can say in this way, like in the fundamental I am talking about, say one is near to the entry of the tube, right? And the two is away from the entry of the tube. But before this, fully developed flow region. Is it clear? Huh. So boundary layer thickness with the length, boundary layer thickness increases. So boundary layer thickness increases. What does that mean? It means that the velocity gradient increase or decrease. No, velocity gradient decrease. Like I am talking about if in this one point, if the velocity at this point is say 1 and here it is reaching, that means after this point all the points have the almost same value. That means it is 5. What is the gradient? The difference is more now. But here at the point this is 2. Sorry. This is 2. Here if it is 1, it is 2, 3. Here it is getting, if it is 5, then the gradient is less. So if the thermal boundary layer grows, the gradient will be less. Gradient is less means this value is, this is gradient na, du dy means this value is less. That means tau will be, okay. How if it is less, tau will be, these two are directly related na. Tau is mu into, now you got it from the fundamental. So two ways how you can solve. One is if you remember this curve, next is through fundamental. So just remember if the you first you tell me whether you understand this concept of understand this concept of boundary layer. Okay. Just I am recalling this, recapping this thing because it is quite essential to understand each and everything regarding this. Hmm. It's a very much complex, not a little complex. So see, if a fluid is entering initially at the entry, whether there is any restriction, no restriction. You talk about air or water, anything is entering. So if the fluid, whatever be the fluid is there, velocity of every layer of the fluid, say it is u infinity. Okay. So once it enter this tube, this is the tube. So it comes with the contact of the wall, right? So because of this, there is a friction. Because of this friction, what will happen? It velocity at this point is almost 0 or tends to 0, and but after this, the next layer, almost this next layer, it is having the maximum value. Only the layer next to the wall, it is having less value. So it is because of the friction this layer is getting affected. Now if I plot this, it will be somewhere like this way. You got it? Now I am taking another layer after a few distance. So what will happen here, similarly as it is near to the wall, its velocity is less, and because of this friction, say in physics, you know, if something friction is going on, the friction in one layer has certain effect on the next layer, right? So now it will suddenly reduce the velocity of the next layer like this way. Two layer or three layer, it will reduce the velocity. After that, it remains almost fixed. So now I will plot this thing. So can you see? Now it is again getting a straight line and now reducing. Similarly, and this thing again after a few distance, it has effect on other layer also, right? So now what will happen? So the velocity is gradually increases and it increases up to the center line. Again from the center line, it gradually decreases like this way. So now if you plot this point, it should be a parabolic profile, fully parabolic, right? So now you just tell me one thing. So where you get this? This is the first point where you see almost after this point almost all this layer having the velocity, same velocity, right or wrong? Here this is the point after which you are getting almost the same velocity, and here this is the maximum velocity at this point, right? And after this, whatever you are plotting, each and every layer, the maximum velocity is at the center. So if you plot here like this way, so if I connect this point from this point, so I am just connecting this point. You got it? Similarly, from here you can also plot. It is quite tough to plot using this pen. You got it or not? This is an imaginary line that connects this point, this point. So at this point, so you see here these two from both sides the thermal boundary layer merges. So that means from this region I can say that it is a fully developed. So that means after this there is no change in the profile you will observe. But before this region, changes in the profile you will observe. Got it? Okay. So try to answer the next one. It is already I have discussed. Please try. UC1 means the center line. UC means the center line. One means the first. Huh? It will. Uh, which of the following? It is true for developing phase. If nothing is mentioned, then you think that it is developing phase. Developing phase velocity will option A. Then how couldn't it be option A? Say U profile you see that initially it is less than it will increases. It is a central line. Though in other point, if you see one thing, if I am talking about the central line, in the central line the velocity increases. But if you talk about any other point, say this point, this layer, in this layer the velocity will decrease. As you move further, in this layer the velocity will decrease because there is a gradual increment. There is a sudden increment, but here there is a gradual increment. So that's why if it is one, if its value is 4, here its value is 3, right now. But in the center line, if it is 5, here it is 6, it should be 7. After that, it should be 7 like that. Now got it? So correct option it will be option C. Good. Now next question. It is true. Why true? Hmm. Because as I have shown earlier, because up to initially it is the inverse of this velocity profile. So the pressure profile initially decrease and after that it remains constant in the fully developed region. So that's why it is true. Good. Next. See, it's a tricky question. Which of the following is or are wrong? There can be multiple options. Options option C is correct. So correct option. Yes, yes, very good. So A, B, and D are correct answer because this is of the profile. We also know that this is fully developed flow region. This is your tau. This is X. So in this fully developed flow region, no changes in tau is observed, so there should not be any increase. So option A is a wrong statement, that's why it is the correct here. Similarly, the option B and option why option D are the correct because option C is fundamentally correct. So it can't be wrong. So option D will be the also answer. So these are the three answer here. Okay. Any confusion up to this, please let me know. Yes. Hmm. Option B, huh? Option B, see, for the section 3 and 4 is in the developing region. It is given in the question. But it is 1, 2 means in the, say, 1 and 2 are in the developing region while 3 and 4 are in the fully developed region. Got it? Hmm. Just a minute. Let me check one thing. This is why it is not working. 1 minute, huh? Please wait. So, Shashwat, have you taken any other courses in NPTEL apart from this conduction and convection heat transfer? In any exam in these courses, whether you will appear from exam? Okay. The rest courses. What are the rest courses? So you have interest in which of the among these three subjects you have interested in which one? So till now, because I think huh, why? IC engine in my I what I remember that in IC engine during my BTech days I have an internship in Tata during the summer, during winter, sorry, in December. So that should be that was in Jamshedpur. So I visited there. So because of this, I find this IC engine subject quite interesting because that internship I have done in my second year, and I got to know about the course in third year. So I was advanced in the course at that moment. You were in third year, right? And what about the manufacturing courses? No, no, I am talking just about your institute. In your institute, so how you feel the manufacturing courses are? So boring among these three, manufacturing, design, and thermal, which one is boring according to you? Hmm. Hmm. Okay. Hmm. So next thing, what is the next question? Just I am showing you one thing. Let me finish this thing, and after that I am showing. Uh, So the next question is the for thermally fully developed flow, the temperature become constant. Is it true or false? Why? Yes, yes, very good. So it should be the only the velocity will remain central line velocity will remain constant, but the temperature, because temperature changes with it depends. So if someone asks you to draw the temperature profile, it depends whether it is heating or cooling, right? So if I talk about this, if this is a thermal bound, and this is a fully developed region. If the temperature at this is a TW, and remember one thing, here there shouldn't be no air arrow. Why there is no arrow in thermal boundary layer profile? Sorry, in temperature profile? Because it is not a vector quantity. So temperature can be constant, it will changes. Okay, so that's why it is false. Good. Next question. So which of the following is or are correct regarding the internal forced convection with constant heat flux condition, assuming the wall is heated. So first tell whether you have any idea regarding this or not. Okay, so let me start with the previous one then. So see, in the thermal boundary layer, I think that you have gone through the lecture by Professor Chakraborty, right? Uh, So here in the fully developed, just I am giving this short details about this thing because time is quite limited here. So for this, a condition is there. This is T minus TW. by T mean minus TW. It should be constant. Theta, say it is theta and theta should be constant. Okay. Here, if I talk about what is Tm, you know Tm? I mean, so I have in the in the classes earlier today, how to find out the mean temperature I have shown. So I will, if time is there, I will show how to calculate using a numerical. So this mean value depends on x. Similarly, this wall temperature also, sorry, this wall temperature is fixed, and this value, this T, this T means a temperature at a point. This should depends on y and x both. But the ratio doesn't depends on x. Got it? Mean temperature depends on x. This T any point temperature depends on x, but their ratio doesn't depends on x because it is a ratio now, so the dependency get eliminated. So because of this, whatever way with what does that indicate? That indicates a profile. Okay. So because of this, the profile always remain constant because what may be the changes in this value. Say if it increases, then this thing should need to be increased, right? So that's why the profile should remain same. So physical meaning, if I talk about its physical meaning, or indicates that if say for some cases if the heat is applied to this wall, okay, this wall if I am talking about, if I am applying heat to this wall, so what will happen? The fluid temperature keep increasing, right, along the channel. If I am applying heat here initially, uh, the fluid is taking temperature heat. So if at this point say the Tm at this point is 50 degree, so at this point what should be the Tm? It should be more than 50 degree because continuously we are supplying heat, right or wrong? Uh, so only the sorry, so the distribution changes. So but the distribution shape or the profile will not change. Only this value will change, but the profile will not change. Say if it is 60 degree, if it is 60 degree, so the profile, though it is a parabolic, it will getting bulge. Initially it was not that much bulge, but as the temperature increases it will get bulge, but it will remain parabolic. So coming to this question, now can you tell this thing? So in this question, okay, not an issue. So say that they are giving constant heat flux. What is constant heat flux mean? Basically means if it is q dash, it should be constant, or in other language I can say it dt by dx should be constant, right? So uh, if you go through these classes where Professor Chakraborty has derived the derivation, this one, sorry. So if for the scenario of P by mCp. So the condition is that this dt by dx by dtw by dx dtm by dx, it should be constant if it's a constant heat flux condition. This thing is derived by Professor Chakraborty in the classes. So I am not deriving this thing, I am just saying. So what should be the temperature variation in the x direction and what should be the temperature variation in the mean temperature variation in the x direction, or the wall temperature variation in the, that should remain constant. Okay. So see, here the heat flux is constant. P is the perimeter. It is the perimeter. So perimeter is also constant. Yes or no? Right. So m dot is constant, Cp is constant. So what that indicates? This from both these two, if you also you remember this thing or from this thing, I can say that this one is constant. That means Tm dependent on, if you do integration, you will get this thing na. So that means Tm depends on, linearly depend on x. So this thing is correct, but the question said which of the following are incorrect. So bulk fluid temperature in exponential. So it is not correct, but as it is told that which are the incorrect option. So according to this question, in this context, it is correct option. Similarly, B is the correct option, and D is also a correct option because bulk mean temperature increases, right? Any confusion up to this? Please let me. So can I move to the next one? Hmm. So which of the following is correct regarding the? Hmm. It is talking about this wall temperature. So for constant heat flux condition, the thing is that dt by dx. Please remember this thing. In the question, it will not be provided this formula. So you have to recall this thing. So, so what will be the answer? Whether first option will be correct or not? Option B. It is correct. Good. Because dtw by dx is constant C1. So Tw is C1x plus C2. The wall temperature decreases exponentially. Wrong. Wall temperature is not constant because it depends on x. So option B. Very good. Okay. Next one concept. this thing, this question, just I am showing this one. After this one question, we will go through a derivation type numerical problem. So this is Great's problem refers to the case of internal force convection in which the flow is hydrodynamically fully developed but thermally fully developed. So you can know what is hydrodynamically fully developed. That means it is talking about which profile? But related to which thing? Which parameter? Fluid flow or velocity, right? So the gadgeted problem means in if a fluid, say in a condition, initially if I talk about this hydrodynamically fully developed flow, you just consider only a flow, only liquid is flowing through a pipe. That is the case of a scenario of a hydrodynamically fully developed flow. If I talk about a thermally developed region, so it relates, say a tube is there. Okay, this tube is closed and water is there. And if you are applying heat from both sides, so if you are applying heat from both sides, then what will happen? Because of the heat, a thermal boundary layer will generate. So this is only thermal boundary layer. If this tube is fixed, and if there is flow, not heat, then it is hydrodynamically fully developed region. But if there is both flow and heat transfer on the tube or the heat supplied on the tube, in that cases it is both hydrodynamically fully developed and thermally fully developed. So in that cases, if I draw the profile, say this is your hydrodynamic profile or the say this is your hydrodynamic profile. Now if you have to draw the thermal profile here, maybe it will start here, maybe, sorry, this black one indicates your hydrodynamic thermal boundary layer and red one indicates your thermal boundary layer. Got it? So see, both are not coming together at a time. So for this, if you know either these two, in which fluid either these two will coming together or not, for this you need to know the definition of the Prandtl number, which gives del by delta T. Del is the hydrodynamic thermal boundary layer thickness. So say this is the thickness of the delta, and this is your delta T. So if both these two, if Prandtl number is 1, that indicate both the thermal boundary layer are equal. That means they overlap with each other. If Prandtl number is more than 1, that indicates that the hydraulic thermal boundary layer is more compared to thermal boundary layer. That means hydraulic boundary layer is achieved earlier, right? Similar is the scenario for if the Prandtl number is less than 1, then the thermal boundary layer is more than the hydraulic boundary layer. So this is the significance of the Prandtl number. Got it? So so if in any problem there is both thermal boundary layer and hydraulic boundary layer, so we known it as gadgeted problem. So the correct option is option A. Okay. So now I am just moving to a numerical problem. Say I am drawing a tube. This is a tube. say the radius is r naught. Okay, this one is z direction and this one is your y direction. Okay, in this question ur is given. Ur means the velocity profile is given as c1 and temperature profile is also given. Ts is c2 1 minus r by r naught whole square. See, this Ts means the surface temperature. The Ts is the surface temperature and C1, C2 are constant. Got it? Two things are given. One is this one and another is this one is given. So in the question they are asked to find you the value of Nusselt number D. Okay. So at this point, say Nusselt number here they have asked you to find out this at this point what should be the Nusselt number. The condition is that let us assume it is a fully developed. Okay. So in this question it is given it is fully developed. So how to find out this Reynolds number? So first, Shashwat, can you tell what is the formula of the Reynolds number? Huh. So it is rho u infinity upon h. No, it is h HLC upon k. L is the what is L? So in case of tube, what should be the characteristic length? Volume upon area. So this volume upon area, so what you will get? You will get is diameter, not volume upon area. It is area upon perimeter. Okay, HD. In case of tube, it is HD by K. So please look into this thing. So what is the diameter here? Hmm. So whatever the value we know, we just put it here. This is small k. Okay. Now the question is that h. So we have to find h, k. They are not given, so I think that k should be replaced as it is. It should be like this one. So now I need to find how to find out this q, because to find out this Nusselt number h, uh, so I know that h is q dash by del t, right? Or you remember this thing, h into surface temperature minus what? Here, what should be the temperature heat flux? Surface temperature minus? No, here the Ts is here in this case. Liquid temperature. So what? So what liquid temperature I need to take? Because it, not central line. Okay, so maybe you have joined the class late, because in such case where there is flow, if someone asked you to find the temperature of the fluid or the velocity of the fluid, you need to find only the average value. And this average value is not like the central temperature divided by 2, sum of the two temperature divided by 2, because as see, if in this region I draw the profile, temperature profile, uh, it should be like this way somewhat. So it's a parabolic profile. So if the variation is like that, how you need to do? You need to integrate to find the T mean. First tell me whether this is clear or not. So from this what I will get? Because in this equation I need H. So from this equation I will get, got it? So now I have to find the Tm. So for the Tm, so if you remember, for this formula of Tm, what you have? M, you remember this thing? Okay, I'm showing this thing again. See this Tm, CPTR into Dm, right? What is Dm? Dm is rho U into this one. Okay, this is energy. See, the temperature is directly linked with energy. So I am just drawing this thing again for you. Just forgot about this thing. I am just showing one thing. See, energy means MCPT, right? Okay. So for temperature, if you need the temperature, means what I need to do? I need to integrate this thing, whole thing. MCPT. I don't know which one will be the changing term, divided by MCP. So also this MCP is there. So which one will be the variable? M dot is the variable. So this is your DM. Got it? So this is your, I can write CP, T means TR into DM dot, similarly by CP DM dot. CP in the question nothing is given about CP. So that means I can consider the CP as constant, right? So integration, the rest thing will be, so into DM. So what is M? M dot rho A V average. You got it? So V average, I don't know V average, that's why I have to U R into DA. I can write now. So I just calculate the first this thing, integration of dm, which is m dot, right? So I just find first your m dot. M dot is rho ur into dA. So rho is there, ur means c1, right? Constant. Area is, what should be the area? Pi, pi r not square, pi r square, sorry. Not r not, no, because it is area. I don't know which area, so I am taking it is r, and the integration is from home to home, 0 to r naught. So this rho c1 will come out, and derivative of this one is 2 pi r dr. Can I write? So what should be the integration? Rho C1 2 pi r square by 2. Value 0 to 2, and ultimately I will get this thing. So it should be pi rho C1 r naught square. So this thing I will get. And another interesting thing is that if you do not put here C, as the C1 is constant, so no need to put this, sorry. So as the C1 is constant, so no need to put this value of dA. You just put it as the best way to do integration here, because C1 is constant, is that just take this value rho C1 integration. I don't know the integration. So what should be the integration of dA? Area, right? So what should be the area? Pi. Same thing. I just do this because here it is not dependent on UR is not a function of R. But if UR is a function of R, then in place of A you need to put pi r square. Got it or not? Yes. Okay. Okay, this is one formula. So you can put this thing and you will get the value. Just I am erasing this thing. Just remember this thing. Rho C1 pi r naught square. Okay. It is getting rho C1 pi r naught square. Is it clear? Hmm. Now the top part, here the integration is TR. What is TR? This one is full one. TR in TS plus C2 1 minus R by R naught whole square into dm, right now. So if this is the dm, so what should be the dm here? Dm should be d of rho c1 pi r square, not r naught, because it is a variable na, so that's why r square. So what I will get, 2 pi rho c1 r into dr. Yes or no? In place of dm I can write, so 2 pi rho c1 r into dr. So rho is constant, c1 is constant, pi is constant. So what ultimately I will get? So this one 2 will coming out 2 r naught square plus integration of this one r into dr. So Ts is constant, right? So just tell me the value of the integration. You want up to this it is clear or not? First tell me this thing. Huh. So see, Ts is there, and integration of rdr, which will be, the integration is from 0 to r naught. So integration is r square by 2. rdr, integration of rdr, because 2 has already come out, plus C2. Integration of C2 into 1 into R dr. That means similarly in case of C2, the integration should be R naught square by 2. Is it clear? Similarly here C2 R naught is a constant. C2 by R naught square. R2 is there and there is R, 3R. Integration of R cube is R to the power 4 by 4. So there should be R to the power 4 by 4. So it will be 2. So what is the ultimate thing I will get? In each one everyone R is there, R square is there, so I will cancel out. So this is your Ts by 2. Okay, let me make it simplify like this way. I just multiply this thing into this one. So I will get the Ts and this one plus C2 minus C2 by 2. So this one is your Ts plus C2 by 2. So what is this value? This is the value of your Tm. The Tm is Ts plus C2 by 2. Okay. So now I can put it here in the H. So can I move to the next one? Just remember this thing. You can tell me Ts plus Tm is your Ts plus C2 by 2. Right? Now H. I need to find out the H. My first objective is the Q dash by Ts minus Tm. So I got the value of Ts minus from Tm. If I put, I got the value of Ts minus Tm, which will be minus C2 by 2. Is it clear? Now I need to find the value of Q. What is Q? What is the definition of Q? Fourier law. Good. Minus Ka. It should be R. What should be the value at R equal to 0 because it is at wall. It is at the surface now. So what is the temperature? You remember this value? You just derivative this thing because I need to derivative this thing now. dt by dr should be what? It should be 0. Ts is constant, right? C2 integration of one derivative of 1 is 0 minus 1 by r naught square into 2r. Okay, so into 2r. Just remember this thing because I just forgot all this thing. What I get? Minus k. What is the integration I got? Uh, C2 minus 1 upon r naught square into 2r most probably. Uh, sorry, r equal to not 0, r naught. This one is r naught. So if you put this one is r naught, so r naught will cancel out So you will get K 2K C2 by R naught. Is it correct? So I can put 2K. Okay, CC. Uh, see one thing. 3 by anything, any wrong I have done? Anything wrong? Yes, minus. Huh. So this C2 by R naught. So there should be 4K by R naught, right? See, why there is a issue, because this negative sign. See, here is a negative sign, here is a negative sign. So the value that is coming out, CS minus TS is minus this one. That means our assumption. So what we have assumed, that Q is Ts minus Tm surface temperature. That means it is not cooling, it is heating. This negative symbol indicates that it is in heating, because the mean temperature is more than the surface temperature. So that means it is a scenario of heating, right? So this negative sign indicates that it is in heating. So you can ignore this negative sign. Okay. And also, or another thing you can do is that you can just replace this one. So no need to worry about this negative sign. So that's why sometimes we just use mod. So you got this thing. Now Nusselt number. Nusselt number, I know that it is H D by K. H I got 4K by R naught. D is 2 R naught by K. Right? R naught is getting cancelled out. K is getting cancelled out. It is getting A. The see one thing. While solving this thing, have you ever imagined the answer will come in numerical? So you understand, the thing is that it is nothing, only this thing you need to know. And another thing you just do, if you forgot this thing, like a CPTR, you can do this thing also. This is another formula, UTDA by UDA. If you use this formula also, you will get the same answer. So it's up to you. Huh? Second formula is coming from this formula. This is the same formula. Use the this one. U means you are temperature profile, and A you need to convert A into R. All these things you need to convert into R. After that you need to do. So also see, I find this thing easy. Maybe some students say that they find this thing easy. It depends on student to student. Okay. So up to this for today's, any confusion? So okay. So with this, Shashwat, please wait 1 minute. Let me bind up this class. Okay. Okay. Thank you. Thank you everyone. If you want, you can leave.